You're working on a crucial project, typing away, and suddenly the screen freezes. The cursor turns into a spinning wheel of death. No matter what buttons you mash, the machine is locked up until you hard reboot. Under the hood, you've likely just encountered what computer scientists call a deadlock. A deadlock is a system standoff where a set of active processes are all waiting for an event that only another waiting process can cause. Imagine your computer has two background tasks running. Process 1 holds your hard drive, but it needs a specific memory file to finish its task. Process 2 holds that exact memory file, but it needs the hard drive. The machine hasn't crashed from a bad piece of code, it is flawlessly executing its own internal logic. Both programs are patiently waiting their turn, creating an inescapable, eternal Mexican standoff. To track which program gets what hardware, the operating system uses a map called a resource allocation graph. A deadlock triggers the exact moment those directional request arrows close into a continuous loop. This trap requires 4 rigid conditions to happen all at once. First, mutual exclusion, meaning only one process can use a resource at a time. Second, hold and wait, where a process grips one resource while demanding another. Third, no preemption, meaning the OS cannot force a program to let go. And finally, circular wait, where the chain of requests forms that unbroken loop. This multi-step requirement is the key to managing them. By designing an operating system to invalidate just one of these 4 pillars, the deadlock trap can't hold. The first strategy engineers use is prevention. This approach writes strict rules that outlaw one of those 4 conditions before a program is even allowed to execute. For example, to eliminate the hold and wait condition, the OS might force an application to request every single piece of hardware or memory it will ever need, right at startup. The trade-off is extreme resource hoarding. An application might reserve a graphics card for hours without actually using it, leaving every other background program waiting on hardware that is technically idle. Total prevention guarantees perfect safety, but it throttles performance so severely that the computer becomes practically useless for modern multitasking. Instead of locking hardware down entirely, the system can use a dynamic strategy called Avoidance, which evaluates new resource requests in real time. This chart shows the banker's algorithm calculating the boundary between safe and unsafe states. Actual deadlocks only form inside the unsafe region. If a request pushes the graph across that line, the program must wait. This strategy has a prerequisite. The algorithm must know the maximum potential resources every app might demand before execution even begins. Predicting exact resource limits across hundreds of active system threads takes way too much computing power to be practical. It is nearly impossible to run this continuous risk calculation on a modern machine. Because prevention is too strict and avoidance is too computationally expensive, operating systems rely on a fallback plan: detection and recovery. The OS lets the computer run wild and only intervenes if a cycle actually forms. This diagram shows how the OS periodically actively hunts for these loops by converting the complex resource graph on the left into the simplified wait-for map on the right. Once a loop is spotted, the OS enters the recovery phase. It acts exactly like a bouncer, violently aborting processes or preemptively stealing their resources to break the chain. For the user, this means the chosen victim process is forcibly rolled back. The application loses its progress, and the computations have to start all over again. Detection trades the heavy overhead of continuous mathematical prevention for sheer brute force. It accepts occasional data destruction to keep the overall machine alive. We've looked at 3 different management strategies, but consider what the operating systems we use every day actually do. They rely on the Ostrich Algorithm. Mainstream operating systems like Unix and Windows simply bury their heads in the sand. They ignore deadlocks and pretend they never happen. There is a mathematical justification for doing nothing. Statistically, the exact conditions required to trigger a true deadlock are quite rare for the average user. Engineers have to weigh the real-world costs. Running constant prevention or avoidance algorithms will permanently slow down your CPU. Compared to that constant drag, a system freeze happening once every few months is a minor inconvenience. Software engineering isn't always about achieving a mathematically flawless system. It is a discipline of pragmatic risk management. Sometimes the absolute best algorithmic solution is just letting the user hit the reset button.